A chemical reaction is a process that chemically converts one substance or set of substances into another set of substances. We call our starting material or starting materials reactants, and we call a new set of substances or a new substance products. We always depict the transformation of reactants to products using an arrow that points in the direction of new stuff that's made. So reactants become products. It's through this arrow that all the magic of a chemical reaction happens. Evidence that a transformation has occurred could include a change in color from our reactants or starting materials to our products or final materials, emission of light or the formation of a solid from mixing solutions together. We call that type of solid a precipitate. We could form a gas when we mix things together. There could be a noticeable change in temperature or even combustion associated with the transformation of reactants into products, to name a few. This is not an exhaustive list, but gives us an idea of some of the common ways that we might experience a chemical transformation. In a chemical reaction, we write an equation that describes explicitly what our reactant or reactants are, what our product or products are, and how many reactants and how many products it's going to take in order to make a balanced equation. Just like making a recipe for a particular final product, a chemical reaction sets out a recipe and all of the quantities of ingredients and final materials that will be prepared once a chemical transformation has happened. In order to correctly write a chemical equation, we need a balanced reaction. A balanced chemical reaction will show us the same total quantity of every type of element on both sides of a reaction arrow, so that we never create nor destroy mass in accordance with the law of conservation of mass. For example, suppose that we were going to react aluminum metal with iron 3 oxide to form the new chemical products, aluminum oxide and molten iron metal. This is a thermite reaction, and we're going to describe it using a balanced chemical equation. The first step towards writing a balanced equation is to write out all of our substances as both reactants and products. Remember that reactants chemically transform into products. Reactants are our starting material or materials, and products are our end material or materials. Our starting materials include aluminum and iron 3 oxide that later will get chemically transformed into new things. Aluminum is just the element aluminum. This reacts with iron 3 oxide. We describe more than one reactant by writing a plus sign in between any separate, distinct reactants. Aluminum reacts with iron 3 oxide. We know how to write down a chemical formula for iron 3 oxide. Iron 3 must have a 3 plus charge. Oxide has a 2 minus charge. To write down the correct chemical formula for iron 3 oxide requires 2 irons for every 3 oxides. Aluminum reacts with iron 3 oxide is depicted by this set of reactants. Now, this reaction forms aluminum oxide and molten iron metal, 2 new substances that must be products of this reaction. So we'll depict that these things chemically transform with a reaction arrow, and we'll write products formulas in the same way that we wrote reactants formulas. Our first product mentioned in this example above is aluminum oxide. Aluminum has a 3 plus charge. oxide has a 2- charge. To balance charges, we need 2 aluminums for every 3 oxides. Lastly, molten iron metal is formed, Fe. This is our chemical reaction. But notice that in this chemical reaction, as it stands right now, there are 2 irons in iron 3 oxide on our reactant side, but there's only 1 iron on our product side at this time. In order to compensate for these differences, we need to also balance chemical reactions. A balanced chemical reaction will be a recipe that shows us precisely how many of each element there are on every one side of a reaction. And what's more is that every side of a reaction arrow must have the same elements and the same number of each type of element. To balance a chemical reaction, I'm going to come up with a list of all of the elements of each type that are present on the reactant and product side. According to the law of conservation of mass, we can't have an element on one side of a reaction and not on another. So, firstly, we've got aluminum on the reactant side. Secondly, iron. And lastly, oxygen. 3 different types of elements on the reactant side. We'd better have 3 different types of elements on the product side, and they better match aluminum, iron, and oxygen. And sure enough, aluminum, iron, and oxygen are the 3 and only 3 elements that are found on the product side of this reaction arrow. In order to balance this reaction, what we're going to do next is count how many of each type of element are present on each side of our reaction arrow. On the reactant side, we only see aluminum in the elemental form. There is only 1 aluminum atom on the reactant side. In the compound iron 3 oxide, there are 2 irons and 3 oxygens. Now we'll do the same thing for the product side. In the compound aluminum oxide, there are 2 aluminums, 3 oxygens. In the element iron, there's only 1 atom of Fe. Our last step here is going to be making it so that each one of these atoms, aluminum, iron, and oxygen, is present in the same total quantity on each side of the reaction arrow. Notice that on the product side, right now, we have 2 aluminums, whereas on the reactant side, we only have 1. How do we manipulate this reaction to show 2 aluminums on both sides, or the same number of aluminums on both sides? We need to accomplish this by using coefficients. Coefficients are numbers that come before a chemical symbol or formula and indicate how many of that element or compound are required or produced for a chemical reaction. In this case, the coefficient in front of aluminum on the left-hand side, the reactant side of this reaction, ought to be 2. In other words, we need 2 aluminum atoms in order to make this reaction happen. A coefficient immediately changes everything about the formula in which it's in front. 2 aluminum atoms change our count immediately for aluminums on our reactant side. We now have 2 aluminums rather than 1. This matches up nicely with the aluminum count on our product side. So aluminums, we say, are balanced. Notice that we have to do something similar for iron, except we have 2 irons on the reactant side, but only 1 on the product side. We need a coefficient in front of the iron atom on the product side of 2 in order to balance it. As soon as we place a coefficient of 2 in front of iron, the count of irons immediately changes on the product side. Now we have 2 irons on the product side, matching up with 2 irons on the reactant side. and we say that iron is balanced. Notice that we don't have to modify anything about oxygen because there are 3 oxygens on both sides of this reaction arrow. Oxygen is already balanced. As a few further examples of balancing reactions, I'd like to talk about the first couple from this balancing equations worksheet. Here in this reaction, sodium phosphate reacts with potassium hydroxide to form sodium hydroxide and potassium phosphate. Making a list of all of the elements on every side of the reaction would require us to think about sodium, phosphorus, oxygen, potassium, oxygen again, and hydrogen on both sides of our reaction arrow. But what I'm going to show you here is a shortcut to thinking about clustering polyatomic ions together that can be helpful in balancing equations more quickly. When we recognize a polyatomic ion like phosphate PO4 or hydroxide OH that do not change form from one side of a reaction to another, we can simply count the clusters of atoms as a whole rather than individual atoms that make up a polyatomic ion. For example, on the reactant side of this reaction, we've got sodiums, we've got phosphate ions, we've got potassium, and we've got hydroxide ions. And we have the same types of ions on our product side: sodiums, hydroxides, potassiums, and phosphates. I'll write them in the same order as I wrote them on the reactant side. And now what I want to do is count up how many of each ion are present in this reaction. On the reactant side, we have sodium phosphate, which contains 3 sodiums. We have 1 cluster of phosphate, we have 1 potassium, and we have 1 hydroxide ion before balancing. On the product side, we have 1 sodium, 1 cluster of phosphate, 3 potassiums, and 1 hydroxide before balancing. Placing a coefficient of 3 in front of potassium hydroxide and in front of sodium hydroxide changes the counts of potassium and hydroxide on the left-hand side to 3 each, because a coefficient affects everything about the chemical formula it's in front of. Placing a coefficient in front of sodium hydroxide changes the count of sodium and hydroxide each to 3, giving us a balance in reactants and products on both sides of our chemical reaction. Next, let's try a reaction that isn't already balanced. In the reaction of magnesium fluoride plus lithium carbonate to make magnesium carbonate and lithium fluoride, we'll make a list of all of the ions that we've got. We have magnesiums, fluorine, lithium, and carbonate. On the product side, we also have magnesium, we also have fluoride, we also have lithium and carbonate. So I can use the trick of counting polyatomic ions here, just like in the previous example. We see that in magnesium fluoride, there is just 1 magnesium cation, but there are 2 fluoride anions. In lithium carbonate, there are 2 lithium cations. There's only 1 cluster of carbonate. On the product side, in magnesium carbonate, there is 1 magnesium cation. There is 1 cluster of carbonate. In lithium fluoride, there is 1 lithium, and there is 1 fluoride. Our job is going to be balancing the fluorine atoms and the lithium atoms in this reaction. We have 2 fluorines on the left-hand side, but only 1 on the right-hand side. Maybe my first approach will be to place a coefficient of 2 in front of the formula that contains fluoride on the right-hand side of my chemical reaction. This changes the count immediately for everything in that chemical formula. It changes the number of fluorines to 2 and the number of lithium atoms to 2. And just like that, we have balanced our chemical reaction. Note that if we don't explicitly place a coefficient in front of a chemical formula, that in all cases 1 is implied. And you never have to write a 1 explicitly, although it's not wrong if you do so.